This conference will now be recorded.
Very good evening, students. So today we are continuing discussions on current electricity. So today we'll be discussing Ohm's law, then resistances like series and parallel connection of resistance, electrical energy, power, etc. We'll discuss today. So let us first focus on Ohm's law. See, if I have a conductor like this, conductor, and if we apply potential across this, some potential V, let us say some battery is connected to this, battery has potential difference or voltage V, and current I is flowing through this. Okay, current I is flowing through the conductor. So Ohm law states that the current in the circuit okay, let me write full, is directly proportional to voltage or potential difference across the circuit, or current in the conductor, let me say, in the conductor, or current through the conductor, is directly proportional to the potential difference across the conductor. So mathematically, what does this mean? This means I is directly proportional to V, or in other way also you can write V is directly proportional to I. V directly proportional to I. Now, as you know, in any proportionality relationship, if we want to make it an equation, then V is equal to IR. See here, R is the proportionality constant. Okay, this is proportionality constant, which is known as resistance offered by the conductor. So this is resistance offered by the conductor. Okay. Now, as you know, we have already discussed somewhat about resistance and all. I'm not going towards, like, see, this has got unit is ohm, right? Ohm, and in symbol this is ohm. Okay, so unit of SI unit of R is resistance is ohm, and it is denoted by omega, capital omega. Okay, so this we have already discussed somewhat now, and also we have discussed how resistance depends on the conductor's dimension, like it is directly proportional to L and inversely proportional to, or inversely proportional to the area of the cross section of the conductor, etc. We have discussed. So what I'm trying to say today, see, let me demonstrate. So we can see here, this is a linear relationship between voltage and current. V is equal to IR. Okay, so I'll just, okay, let me just go to the, let me erase some of these things. Okay, so this I'm doing because I have few figures to explain here. Okay, so V is equal to IR. So we can see that V and I, they are directly proportional to each other. So if we plot V and I, either I as a function of V or V as a function of I. Okay, so V as a function of I, if you plot, let me write it here. V is equal to IR, Ohm's law, and we are plotting V versus I. We are plotting V versus I. Okay, V versus I. So this plot, how does this look? Like it will be a straight line, and also it will go through or pass through the origin, as you see. So current and voltage, as see, I can say here, current and voltage voltage has a voltage have sorry, have a linear relationship. Okay, a linear relationship. Now see, V by I, if I just get the slope of the curve, V by I, this is nothing but the resistance. So slope of V versus I curve is equal to V by I is equal to R. Okay, so this gives the resistance. Okay, resistance. This gives the resistance. So slope V versus I curve, slope gives the resistance. Okay, see, there could be some materials which may not follow Ohm's law, or there are various metals also which may not follow I should not say metal, some material. Okay, some material like semiconductors. Okay, semiconductors, they do not follow this linear relationship between current and voltage. Josephson junction, which is used in SQUID quantum design, like quantum interference happens in Josephson junction. So those are actually quantum or quantum objects. So quantum phenomena is observed, and in those cases, actually, even in case of superconductor also, you will not see current voltage linear relationship. So specifically in diode, transistor, etc., current is not following, like current and voltage, they are not directly proportional to each other. So you look the devices or conductor or metal conductors which obey Ohm's law. Ohm's law are called the ohmic conductor. Ohmic conductor. Copper, silver, iron, etc. So these are all ohmic conductor. Okay, these are ohmic conductor. Or the devices where, again, the devices in which V and I have a linear relationship or V and I obey Ohm's law. Obey Ohm's law in devices like electric bulb, etc., heater, etc. Ohm's law are called linear devices. Linear devices. Okay, so this is about Ohm's law and the conductor which are obeying Ohm's law. They are called ohmic conductors, and the devices in which current and voltage has linear relationship, or current and voltage obey Ohm's law. Like, see, I can give bulb, electric bulb. There it is followed. Okay, electric bulb, then heater, etc. Some examples. So their current and voltage linear relationship is being followed. Okay, so these are called ohmic conductor, ohmic devices, and linear, or sometimes they are called linear devices. Okay, but we obviously will encounter some cases where the current voltage relationship is not linear. See, this is a parabolic relationship. So current voltage relationship current and voltage relationship is not not linear. Okay, so this is non-linear curve, you can see, which is passing through the origin, but this curve is non-linear, whereas this is linear curve. Okay, all right, so we can see where Ohm's law is valid, like V is equal to IR. In that case itself, we'll be able to find out resistance from the slope. Like in this case, we cannot find out so easily. Okay, so easily in the sense we may not be able to also find out this. Obviously, we'll get this slope at each point. Like this point we can get the slope. This point, since the slope is changing, so the resistance also will change with that slope. So that's why there is no linear relationship between current and voltage in case of certain material like semiconductors, diode, etc. Okay. So here you look, in case of Ohm's law, we have seen for a particular V, there will be particular I, right? V1 for particular I1, or we'll get V2 for a particular I2. Okay, like that. That means for each value of voltage, there should be only one definite current, isn't it? In case of Ohm's law, that we have seen, if you just look back, see, for a particular value of voltage, there is a current, particular value of current. Okay. So in case of diode, see, this is forward bias of diode. So forward bias of diode, and this is actually reverse bias current. This is actually reverse bias. Okay. All right. So in this case, you look this. Obviously, this is a linear, not linear portion. Okay, at very high voltage, maybe there could be some linear relationship. But in this case, look, voltage and current. In some cases, voltage and current, if they are varying like this, then they are not obeying Ohm's law. Not obeying Ohm's law, because see, I have, for the same current, I have two different value of voltage. Okay, so there are two different voltage for a same current. Okay, which is not possible. Excuse me. So there are two voltages, V1 and V2, and this is some I1 current. For a particular current, I said, for a particular current, there will be corresponding voltage, and that will be single valued, not double valued and all. Okay, but we can see here that the current voltage relationship is such that for a single value of current, there are two different voltages. Okay, so this is not valid in case of ohms, like ohmic conductor. So these are actually called non-linear conductors or non-ohmic conductors or or non-linear materials or non-linear devices. Okay, the devices where Ohm's law is not valid, it is called actually non-linear devices. Okay, like diode, triode, transistors, etc. So in this case, it is seen here. See, this is non-linear region. So this side is also, this is non-linear region, and see, this side it is said slope is positive, this side negative. So somewhere positive resistance, somewhere negative resistance, which is not possible. Okay, so that means what I'm trying to say, that, so this is actually for gallium arsenide, Ga arsenide, GaAs, I think. Anyway, so this is semiconductor devices or semiconductor material which shows this kind of behavior, current voltage relationship. So this is non-ohmic. Okay, this is non-ohmic. Now see, we have seen V versus I curve. So in this case, suppose we want to find out, this is I, this is V. So slope will be I over V. So slope will be 1 over resistance. Okay, so that you have to remember. So here I have a very simple problem. you can see here that this is I versus V curve, and also the devices for which this is drawn, current and voltage, they are following linear relationship. Okay, linear relationship. As you see, the current, see the curve is going through the origin. That is very nice. So this is for ohmic conductor or ohmic material or ohmic devices, ohmic or linear devices. Here, what is the question? Question: current voltage graphs for a given metallic wire. Metallic wire. Okay. Uh, Two different temperatures are T1 and T2 are shown in the figure. Temperature T2 is greater than T1. Is this statement true or false? That means it is said that T2 greater than T1. Is this true? Is this true? Is this true? So this you have to see here. Say I know that resistance has direct relationship with temperature. Okay, now see here, if we just get the slope, so slope will give resistance generally in case of V versus I curve, but in this case I versus V curve, so slope is I over V, that means 1 by R. Okay, 1 by R. And you look here in this curve, see this T1 temperature, this curve has got more slope, okay, and this has got less slope. So more slope means what? Here more slope means what? See, more slope means 1 over R. This value is more. Okay, so more slope means actually 1 over R, that value will be more. This will be more in this for this curve. So in this case, look, we know the R versus temperature. R is directly proportional to the temperature. Then 1 over R will be directly proportional to 1 over T. So that is very nice. So in this case, see, this has got more slope. That means this has got more slope. That means current is more through that. I'm sorry. So if this is more, this temperature 1 over T also will be more. That means, okay, anyway, let me just check from here itself. So resistance is equal to 1 over slope, right? 1 over slope. 1 over slope. So if this is having more slope, then resistance R1, corresponding resistance is R1, this is having R2. Obviously this will be less. So R1 is less than R2. This indicates. And we have seen R is directly proportional to T. So T1 will be less than T2. Okay, so this kind of question may come like simply like it will be drawn and you have to answer like which one has greater resistance, etc. Question will be there. Okay, so now what we'll do, we have already learned about Ohm's law. We'll see quickly we'll see where Ohm's law is not valid. I have already shown you, I think I have already shown. Let us just go to the another topic. So series and parallel combination of resistors. So in circuit, sometime we may need to use high resistance, very high resistance, very high resistance, or sometime maybe we have to use very low resistance also, very low resistance. So very low resistance we may need to use. Very high resistance and low resistance we may have to use, actually we may have to use conductors with very high resistance or sometimes very low resistance. Okay, so when you need, see, is a very high resistance, a single resistor may not be able to serve this purpose, or may not be able to give you that high resistance, that high or low resistance. Okay, so very high or low resistance cannot be obtained from a single resistor. Okay, so for that, we need to use a combination of resistors to get that particular, or get that like required potential, sorry, resistance for the circuit. Okay, so to get desired resistance, low or high, we need to use combination of resistors. Okay, so then we have to learn how to find out equivalent resistance of a combinations of resistors. And let us try. So there are two types of combinations. One is series combination, main or basic two combinations, two types of combinations. Okay, and another one is parallel combination. Parallel combination. Okay, see what happens in case of series and parallel. So suppose I have let us take two resistors of resistance R1 and another one has resistance R2. Now if I add them or connect them in series, see how to connect them in series. They have to connect end to end like this. End to end you have to connect, and then you can connect it to battery in a circuit. Now see, this has resistance R1, this has resistance R2. If the battery voltage is V, or potential difference across the terminals of the battery is V, then in this case, look, there will be a current as soon as switch is closed. So current will be there, and you can see the same current according to conservation law of charges. Same current will flow here. Same current will flow. Whatever current is coming out from the battery, the same current will flow here also. Same current will flow here also. Same I current will flow. Okay. So in this case, see, current is not divided in this series combination of resistors. But what, if you are able to find out the voltage across R1 is V1 say, and voltage across R2 say V2, V2, then the total voltage is actually the sum of these two voltages. Okay, so if we see from Ohm's law, if we write V is equal to IR, so V is equal to IR, so V1 is equal to I1R. So here V is equal to, suppose I current I is flowing, so this will be I into R1 plus I into R2. Okay, so I into R. So this right hand side, let us say after using this combination of resistor to this circuit, if I replace this circuit with a single resistance of equivalent resistance, R1 plus R2 here. So if I use an equivalent resistor which has resistance R1 plus R2, and if this combination of the resistors are connected to the same battery of voltage V, and for that reason, let us say the same current is flowing through that, then we can write V is equal to IR. Okay, so if this we put it here, this in place of V, so R equivalent. So II goes off. So we can see R equivalent in case of series combination of resistors, so we get equivalent resistance is R1 plus R2. This is in case of series. We'll discuss about the parallel combination. So parallel combination of resistors. Okay. In case of parallel combination. So in this case, see, students, you should remember one thing, that is voltage is divided in case of series combination of resistors. Voltage is divided. Okay, voltage is divided here. So series combination of resistors is resistor is sometimes called voltage divider. A voltage divider. Okay. All right. So in case of parallel combination of resistors, let us see parallel combination of resistors. Suppose I have the same resistor. I am connecting them like this. Suppose this is point A, this is point B, and they are connected to a battery. Current is flowing from A to B like this. Okay. So we see here that when current is flowing like this, suppose I current is flowing and V is the voltage. So I current is flowing from the flowing out from the battery. We can see after coming here at this point A, current is actually getting branched into two. Current is getting branched into two, or it has two paths to flow. One is this path. Let us say there are, see, let us say this is I1 and this is I2. So throughout this, it will come up to here I1, and throughout this it will be I2, and it will come here up to this junction, this, and then the current will be added up here. So here it will be I1 plus I2. So if the condition is like, see, in this case, you know that current is actually getting divided, current divider. So parallel circuit is called current divider. So you can see that current divider. So in this case, so what I can do, I know, see, A and B are having the same, see, they are across the same, A and B, they have potential difference V. V for both of them, the potential difference is V. Both the resistors R1 and R2, their endpoints are connected to the same point A and B, and A and B are connected to the battery terminals. So we'll so I1 plus I2 is equal to I. Now here, what is I1? So V by R1, and this is plus V by R2, and this is equivalent current for equivalent system with the same equivalent resistance. So here you can see, if we, so 1 by R equivalent, this is equivalent 1 by R1 plus 1 by R2. 1 over, so this formula you might have seen in case of conductor, like static conductor. I'm sorry, this is plus 1 by R2. Anyway, so you can see here the current is getting divided. So this parallel circuit is called actually current divider circuit. Okay. Now, if we go with many number of resistors, then see in series combination. Okay, let us say RS series combination. So R1 plus R2 plus R3. Okay, it can go up to a number. Now, equivalent resistance 1 by R equivalent is equal to 1 over R1 plus 1 over R2 plus 1 over R3 plus dot dot, it goes up to this. Okay, so this is a voltage divider series, and this is actually for current divider. Current divider. Okay, so we'll stop it here for today. Next day onwards, we'll take up numerical problems, etc. Okay. Thank you for your patience. Bye for today.